We just did a practical. So just grab your science book out and take some notes if you want. Someone is recording it beneath. You can actually go back and watch the recording. Okay. So we know from this practical what we were trying to prove is the law of conservation of energy. Energy can't be created or destroyed, so the energy that the ball had at the top of the ramp must be the same as the energy that the ball had at the bottom of the ramp. So we're going to do a calculation now, and I'm going to show you a few things. I'm also going to put in here a section on conversions. So which group wants one of their calculations done for them?
Yeah, right, yeah.
Okay, Brock, you're the first person to put your hand up. Well done. So can you tell me your golf ball, please?
Golf ball weight.
I need to know a couple of things. So for the golf ball, just start off by telling me the weight.
The weight, doesn't really go here is it? Where's the golf ball? 21.7 grams.
Okay, so 21.7 grams is not acceptable because when we find EP, we need to work in kilograms. So to get from grams to kilograms, we need to understand this K. It means kilo, and kilo means 1,000. Excellent. So if you didn't know how many grams are in a kilogram, you do now, just by the name of kilo. It tells you there's 1,000 grams in it. So how many meters are in a kilometre? 1,000. Brilliant. How many litres in a kilolitre? 1,000. 3. Now to get from grams to 2 kilograms, I need to actually divide by 1,000. That's where the number comes from the word kilo. And so if I divide this by 1,000, then a couple of things are going to happen. Now, number one, what's going to happen is this decimal place is going to move 1, 2, 3 spots. And that's because our place value system is made up of units of 10. And there are 3 zeros there, so 3 place values backwards. The reason we're going backwards is because when you divide a number, you make it small. So the decimal point is now here. The only problem is there's nothing there. But I put a 0 because that's how I represent nothing. So 21.7 grams, if I divided that by 1,000, would actually equal 0.0217 kilograms. Okay, so that's the first thing I need to do to find my mass. So I know it's 0.0217. I would probably definitely write this down if I didn't know how to do it, because it's important. G. Who measured G? Good, because you didn't have to. What was it?
9.8.
9.8. Brilliant. Excellent. 9.8 metres per second squared. And because I'm doing your results, I need to know your height.
Oh, it was 82 centimetres.
Okay, so that's also a problem because I don't measure height in centimetres, I measure it in meters. So, here we go. Let's talk about the word centi. What does that mean?
100.
Yeah, so century. So how many centimetres are in 1 metre? 100. Brilliant. So what am I going to divide this 82 by? 100 and I get 0.82. So my height is 0.82. Someone times those numbers together for me, please. Did you round that, please?
The rounded is 0.174
So that's the rounded version?
from 0.1743.
Okay, thanks. That's all I want to know. I'm going to talk about that later. And Jules. All right. So, what should DK be equal to?
0.174.
Good, shouldn't it? So it is. How do I find DK?
Half and
That's the V bit, but yeah.
half
Okay, so to get this, we need to do speed. How did I tell you to find V for speed? It was what?
distance divided by time.
Now, did we know the distance? I made you measure it. And time. So how many times do you have for this ball?
Oh, we have 3, but we did it to 2.07.
Did you average your time?
Yeah, that's average.
Can you give me the 3 times? Because I want to show the averaging time.
2.20, 2.07, 2.07.
22.
2.20.
Yeah.
2.07.
Yeah.
And 2.07 again.
Thank you, bro.
You're welcome, mate.
That was lovely. How am I going to find an average of this?
Add them all together.
Oh. Sorry, so a little spit then. 2.2 plus 2.07 plus 2.07, and then I divide them all by
3.
3, excellent. And the average when you did it was what, bro?
No, 4.96.
2.4.96?
No, it's just 4.96.
That's not right.
Adding them together.
Did you add them or times them?
I added them and divided them by 3.
Okay, so you got 6.34 divided by 3.
I should calculate it.
It's going to be 2.6. No, can't be. What'd you get?
2.1.
2.1. I'm glad someone did it. Thank you, Zach. I know you did it too. So I'm going to divide this by 2.11 because that's going to tell me my speed. What was my speed then? So I'm dividing 2 by the average I just found. What will my speed be?
0.95.
0.94 meters per second. Brilliant.
0.95.
0.95 then. Okay,
Because
let's not fight. Let's not fight. Okay, so a half is 0.5, agreed. Mass of the ball was 0.0217 and the speed was 0.95. And what do I need to do to that?
Square it.
Excellent. Square it. So if you put all those numbers in and do that, we should get the answer of 0.174, shouldn't we? Let's find out we do. What answer do we get is what I'm waiting for.
0.097.
I got 9.7921.
0.097. No, that's not rounded this time. Oops. What's wrong? They're different.
I got 9.79.
Why? Well, technically speaking, you should basically have told me that this was never going to be the case. Because every time you rolled that ball down the ramp, what did you do? What did you hear? Yep, you heard sound. What's that mean?
Energy loss.
It means that there's energy loss. So these two numbers are never going to be the same. Also, too, there are so many errors in this practical because I designed it to have many. And we're going to talk about them now. And then the rest of this lesson, you are going to sit with your group and you are going to tell me how you're going to redesign this experiment. Tito, join one. Here we go. Okay. So, the problem is manifolded. This is our 2 meters, isn't it? Okay, so when we did our speed calculation just a minute ago, what did we use as distance? We used 2 meters, didn't we?
But that's not really the difference.
But the ball didn't travel 2 meters. Because you did it from up here, because I told you to. And so it's travelled this bit, and it's travelled that bit. So what's the problem? Did it travel 2 meters?
No, travel more.
So the calculation or the way that I'm getting you to calculate it is always going to give you the wrong speed, which means that these numbers are never going to be the same. Okay? Now, I actually designed this experiment to be wrong. Because the idea behind anybody being a scientist is that you do an experiment that will be wrong, and then you will take your results and you will do it again. So you guys are going to try and see from your calculations of whether or not you can get closer than my practice. So can you get these two numbers closer? All right. So one error was our calculation, our speed calculation. Anybody think of another?
Will the energy loss?
Energy loss, yeah.
Air resistance.
So you're losing air, you're losing energy through friction. That's definitely one of them. So friction. We're losing it through sound, and someone said it over here. Air. Yeah, because that ball is going to push all the air out of the way as it rolls down that particular ramp. Now, where were some other errors, do you think?
When you drop the ball, it might not always be at the same place.
The ball drop, yeah. So did you drop the ball at the same place every time? I can tell you didn't. The other thing, so at the same place, is did you give it any kind of angle? So I saw one kid who basically let go of the marble, but the marble actually went straight into the side of the ramp and then just bounced the way down. That was last class. So that person had actually given it a little bit of force when they dropped it. So the ball drop is incredibly important. And did you impart a force? Did you give it force? Because if you push the ball down the ramp, then that's different than the ball just sitting there and rolling down, isn't it? Because you've actually given it a little bit more force or a little bit more energy at the current. The other thing is friction of the ramp, but what else? What else did it roll along? It didn't just roll along the ramp, it rolled along the carpet. Is the difference in friction big between a carpet and a ramp?
Yes.
Yeah, that ramp is fairly, like it's dusty, so some of that dust might be a problem, but the ball will roll down that ramp a lot quicker than it will roll across the carpet. The other thing at the end of the ramp, who noticed that ball bounced? Okay, so you had a bounce at the end of the ramp. But fundamentally, why is this wrong? You measured the ball here. Is that where it has its max EK?
No.
Where does the ball have its maximum kinetic energy? So tell me when to stop.
So,
There, doesn't it? Remember the hill?
Yep.
Yeah, this is where the ball has the maximum kinetic energy. So why, in fact, as we go through, is the ball gaining or losing kinetic energy as it goes through this? Losing it. So that 2 meters at the end makes absolutely no sense. Okay? The other thing is how accurately did you measure it? I saw a few kids do this. Yeah, it's about 2 meters. And then they whack something on the end of it, like a ball or a pen or something along those lines. And they, of course, just did they move? The other thing is, did you move the ramp? Because if you move the ramp, you change the angle. Another thing is, where did you measure your height from? Because the ramp itself is very thick. So the ramp has a thickness of about there, and if you just measured from the table to the thing, have you measured your height properly? No. Did you measure to where the actual ramp starts, or where you placed the ball? There are so many errors in this practical. Number one is it doesn't even make sense because fundamentally it's wrong. We're not measuring maximum EP, we're actually measuring, maximum EK, we're actually measuring EK a lot further away. Fundamental error in design. Now, I did this because now what I want you to do, I haven't finished yet. Are there any other errors in our calculation? What did we do? Did we round?
Yeah.
How many times have we rounded by the time we get back to this one? We've rounded a lot, haven't we? Now, rounding's not a problem, but it's getting us further and further away from the actual experimental data that we have. So while we have to do it mathematically, we are giving ourselves a little bit of an error in that rounding particular thing. Anybody think of any other errors? I'm sure there's one I've forgotten. No? Okay. So what are we going to do? How are you going to make this better? Well, what I want you to do now is sit with your group, and I want you to tell me what errors you can get rid of. So, if you redesign this experiment, do you need the ramp? So probably the simplest way I could redesign this experiment is get rid of this. Now, if I get rid of this 2 meters, what errors do I get rid of here? Well, basically, the fundamental error that it's never going to work is a big one. Do I get rid of the bounce on the end of the ramp?
Yes.
Yep, because I'm not going to measure it. Oh! Sorry. Timing error. Zachary, me and you were playing with those stopwatches, weren't we?
Yep.
What was the quickest that we could turn it on and off?
Probably like 10 seconds.
Yep. 10 seconds was the quickest that we could actually go. Like that. Turn it on, turn it off. If I say go to you, then this is what happens. So you're sitting there with the stopwatch, the person with the ball is dropping, they let go and they say go. Now, it takes time for sound to travel to your ears, not very long, but then it's got to go into your brain, and then your brain has got to say, I need to press my thumb down. That is a timing error. Okay? You'll never be able to get rid of it unless, of course, you start to turn to some more advanced things. We do have some. So you've got your pocket labs over there that you can use. Did anybody notice you noticed it, the little thing I was playing with, the little black box that's there? That's a speed thing. So you can basically drop a marble through it and it will measure the speed for you. You don't need to do the calculations, you don't need to do anything like that. And it's got 2 lasers in it, so is it more accurate than me?
Yeah.
It is. So if you want to use something like that, you're more than welcome to. The Pocket Labs measure all kinds of different things. We'd have to play around with them, but I'm more than happy for you to use them if you want. So, if I get rid of this 2 meters, do I fix my calculation of speed? Yep, it's no longer wrong. If I just use the ramp and measure from there to there, how am I going to get rid of friction?
Not all of it.
No, I can't. I can't get rid of friction because, of course, it's got to roll down the ramp, doesn't it? Can I get rid of the sound loss?
No.
No. And can I get rid of air resistance?
No.
No. But I have managed to get rid of this error, and I've managed to get rid of this error. Can I get rid of the ball drop error?
No.
Can I?
Yeah.
If someone's going to drop it from here?
Well, why don't you just place it on the ramp?
Okay, so we can maybe adjust it. I don't know if we can get rid of it though. The bounce at the end of the ramp, well that's gone because we don't have an end of the ramp. And the fundamental thing is error in design. Can I get rid of timing error?
No.
No. Okay, so I'm just like there are some errors I'm just going to have to accept. I'm going to have to accept air resistance. Sorry, I mean across there. I can't get rid of it. Or could I? We have a vacuum pump at school. If you wanted to mess around with the design, I'd be more than happy for you to do it. We could suck all the air out of the cylinder and we could just drop a ball. Now, if I do this, I'm going to regret this, I'm going to have to pick it up. Would that do the same thing?
No.
Are you sure? If I could work out the height of this, would I know it's EP? And if I could times it before it hit the ground, could I work out 2K?
Yeah.
So what does that get rid of?
Friction.
Yep, it gets rid of friction, it gets rid of sound, it gets rid of air resistance, it gets rid of this calculation of speed because I'll measure the distance. It doesn't get rid of my ball drop, but it's a little bit more accurate because I just have to let go of it. Does it get rid of the bounce? Let's get rid of the fundamental error in design. So let's show you 2 ways that you can redesign this practical. Does it get rid of air resistance? No. Okay, you can't necessarily, but I can get rid of friction, I can get rid of sound. So the idea behind this whole experiment is that you can do better than I do. And that my design for my experiment, I've already been able to see is this a good experiment?
No.
No, not at all. I mean, it's a good experiment in the fact that it's shown me what I need to get rid of and what I need to think about when I redesign the next one. And this is what science is. It's about that change and basically forming an experiment that may lead you nowhere, but will ultimately lead you to the next step that you need to take to actually solve this problem. So, the reason I'm giving you this lesson, now I'm going to go back over all of this on Wednesday. Alright? So Wednesday's lesson is going to be made, it's going to be a big one. I'm going to show you once again how to do the calculations. I'm going to show you what I want it to look like. I have an exemplar, so you're going to be able to read someone else's from last year. But for the next 20 minutes, you need to redesign this experiment, and I need a list. Okay? Because I can't, don't come to me on Friday and say, oh, I'm going to need a nuclear reactor, 4 microscopes, and a dead child. Okay? Because number one is, I don't know if we've got 4 microscopes. What?
Do you actually get a dead child?
No, never. I would never get a dead child. Yuck, I would pick up anything like that. It would be horrible. Now, the whole point of this, though, is I want you now to redesign. How are you going to get rid of as many of these errors as you can? Now, you're actually doing one of your paragraphs, so write down what you do. So if you're going to say, I'm going to get rid of the ramp, then write down for me why. What does getting rid of the ramp do for you? What errors does it get rid of? Also, too, I've identified all these errors. Can you guys identify any more?
No.
Wow, there's just one glaringly large error. Yep, if you weighed it wrong, because a lot of people like, did you get the ball right in the middle of the scale? So we'll weight one. But what do warm bowls do?
Oh, they have weights on the inside that direct which way they go.
So did that ball, when you did it, does your ball, or every time you dropped it, did it travel in a straight line?
No, because the weight on the inside.
Yep, we'll make it actually do this. So is this a further distance than that?
Yeah.
Which one's bigger? The slanted one is, isn't it? Because it's the hypotenuse of of a right angled triangle. So this side must be bigger than that. Now, who had a ball that hit the side of the ramp and bounced off a couple of times? So that has not travelled the 2 metres that we worked out. This 2 metres is a disaster, really, isn't it? Because unless you could get that marble to go in an exact straight line for 2 metres, it hasn't travelled 2 metres, it's travelled further. The lawn bowl will actually, I don't know if you noticed, but sometimes it'll actually taper off like that. Once again, giving us a much bigger distance than the 2 metres that we did. So that's a massive error. Isn't that sad? What about the golf balls? Why do you think I chose that ball?
It's got bumps.
It's elastic, yeah. And so basically as it hits the side of that, you're getting an energy transfer from kinetic to elastic potential and then back to kinetic. So yeah, the type of ball. Do you need to do 5 balls or 4 balls?
No.
Does that make any difference to your experiment? Which one do you think was the best ball to use? The marble. I agree. The Nerf ball, the big one, rolls down the sides of the actual ramp. It doesn't even touch the ramp. It actually rolls down the side casings. It's too heavy to measure, and it's very, very light, so it'll be affected highly by air resistance. If we looked at the lawn bowl, we already know that's not the ball to use because it does what? It's got a bias on it, yeah. Tennis ball, yeah, you could use the tennis ball. Yeah, it's got a little bit of elastic in it. Why is the marble the best? Also, too, it's very, very what?
Small.
Small, which means that it doesn't have to push as much air. Yeah, it doesn't need to push as much air resistance. What's that? The marble weigh? I don't know, that's why I left a set of scales. Anybody know how much the marble weigh?
4.7 grams.
4.7 grams, there we go.
I wrote 5.8.
Now, I'm going to stop talking. You've got 15 minutes to redesign this experiment. If you want to come and talk with me about it, you can talk to me on my whiteboard table over here. But you've got 15 minutes to redo this. And if on Friday you turn up with no redesign, you're probably just going to sit in this room for 35 minutes and then fail. Yeah, you can go talk. Let's combine Really?